Hello everyone, I'm Lucas Campos and today I'm introducing Physics 2211 Lab 2, Motion of a Falling Object. Getting started today at our agenda, we're going to start off by looking at the introduction and show the purpose of the lab, then go along to the fundamental principles used, and then the data analysis and comparison, moving into possible errors and finishing with the discussion questions. Alright, so introduction of the lab. So in this lab, I observed a paper ball drop through the air with drag, and then I got the data from Tracker program, and then I used Go script to compute drag and gravity models, and then a model with only gravity, and then I compared those models. And my initial conditions for this lab was I measured out the height at which I dropped the ball from, which was 1.3 meters, and time is initially starting at 0 seconds. All right, fundamental principles used within the lab. We have momentum and Newton's second law. We have the net force is equal to the change in momentum divided by the change in time. And we have the constant acceleration in the y direction, which is just negative 9.8 meters a second squared. And we're using F equal ma, Newton's second law. And we're just overall demonstrating the force of gravity on a falling object. All right, and here's the application used for the lab tracker. You can see here I dropped a paper ball through the air, and the system is the ball, and then the surrounding forces, which is drag force. And tracker then computes a graph of the position time graph, and you can see here it's kind of a downwards curved slope, and that just indicates gravity and drag force acting on the object. All right, and here's the GlowScript code used for the lab. I made two models, one with drag and gravity, and then the other one just gravity with no drag. And we can see here at the one with drag, the proportionality constant for the magnitude of the drag force is calculated out to be 0.277, and then the one in no drag does not use that. It's just 0. And then I changed here the force of gravity is equal to just the y component is negative gravity times the ball of the mass, and then everything else is zeros because we're just working in the y direction. And we have the drag force is equal to b times the ball speed squared times j hat, and the ball speed is just the square root of the ball velocity of the y component squared. And then net force is force of gravity plus the force of drag. And here the momentum principle, it's just velocity update formula and such. The ball velocity equals the ball velocity initial plus net force divided by ball and mass times change of time. And then in the no drag model, moving over, there's no drag force, so force of gravity is just equal to the negative g times uh, the ball mass times j hat, and then also in both of these, j hat is just 0, 1, 0. It's just pretty standard. And then in the no drag, we have the net force is just equal to the force of gravity. And then same thing here, it's just velocity update formula, just ball velocity final equals ball velocity initial, and then plus net force divided by mass times change of time. Cool. And so now looking at the comparison within the two, we could see that they, for the most part, remain the same, but then towards the end they start to deviate more as so the one with drag and gravity, it's moves down a little bit slower, and it's because drag is an upwards acting force, and it's working against gravity, so it's gonna change this. And obviously, like as if time were to go on here, this gap would become bigger and bigger. All right, and possible errors within the lab is just the tracker application. It read like the center of mass, it read a point mass, sorry, through space and time, and that can kind of mess up. It's a program. I can't completely accurately track that, and also just potential inaccurate drag force, just stuff like that can just like kind of change it ever so slightly or deviate the true answer just a little bit. And then some further discussion questions is which model is terminal velocity reached in? And we can see that terminal velocity occurs with drag force, and it's seen in the computational model. And this is when the net force is approaching 0. Its terminal velocity is when the drag force is equal to the gravitational force, so then net force is equal to 0. And we can see here it didn't quite reach it, but just about here. It levels out about right here if this imaginary line continued on. And then next question is if the object was given initial velocity with terminal velocity change, And terminal velocity is not dependent on initial velocity, so it'd be the same as if it began from rest. So even if you threw it down a little bit, eventually it would reach the same terminal velocity. Awesome. So thank you. This wraps up the lab. In this lab, we modeled drag force acting on a ball, and we used the tracker model along with computational models to view this. Yeah, thank you and have a good day.